jump right in. Ow. All particles of a substance have the same kinetic energy. True or false? False, right. So which particles, if I had, let's say I had a bowl of soup. If I had a bowl of soup and you pick up the spoon, you start to blow on it to cool it down, what are you actually doing to the soup? Huh? What are you slowing down? What's coming off the top of the soup? Steam, water vapor, right? Really, really, really hot, high kinetic energy, water droplets. What are you doing to them when you go like, where are they going? Huh? Back in the soup, that would make the soup hotter. You pick up the soup, you pick up the soup spoon, and you blow on them. Where are the water particles going? Away, right? They're just going away. So literally what you're doing is you're taking the particles that are the hottest, the ones that are vaporizing, and you're blowing them away from your soup. So overall, the soup gets what? Cooler. Because you're taking away the hottest particles, the highest kinetic energy ones, right? So all particles have the same kinetic energy? False. Because we have a big range of kinetic energies. Really, really slow particles to really, really hot, fast particles. Definition of temperature. We talked about this last unit. Anybody? The average? Right. The average kinetic energy. So this is AVG, sorry. Temperature is equal to the average kinetic energy. That is a definition you absolutely must know. Name 3 kinds of motions that a particle can have. This one you may not remember. But give me one that you know that a particle can do. It can do what? Vibration. Literally, the definition of vibration. You ready? Wiggle in place. So just vibrate like this, right? So the wiggle in place, that's one of them. I don't know, I love that definition. So vibrations, and then what about this one? Sliding is also called translating. So translation or translate. Translate. And then this one. Rotate. Okay. So particles can do all of those, and that's all considered kinetic energy because it's all energy of motion. Now, the next couple things, actually, we read a little bit about. We talked about how particles can collide with another one, and they transfer their energy, kind of like Newton's cradle, little, the beads that go like this. So they transfer their energy. Some particles move fast, some particles move slow, right? Now, we need to talk about that in a more graphical way, and how we can determine the energy of such particles through a heat curve, okay? So the heat curve, we talked about this last unit, but we're going to use it this unit as well. Let's talk about each of these pieces. Okay, so what did a heat curve look like? Steps, right, look like steps. And I want you to draw yourself one with temperature versus time. Let me scroll this back up, Maddie. There you go. So draw yourself a heat curve. And I want you to start off with a slant. Starting with a slant, then plateau. Slant, plateau, slant. Just need to give myself a little bit of spacing.
Good morning, staff. If you would please be sure that you are signed in at this time. We're trying to find out who isn't here. Again, if you're here and have not signed in yet, please do so at this time. Thank you.
I have signed in. Okay, so you should have something like slant, plateau, slant, right? What is the very first phase? Solid. Next phase, or what's happening here, excuse me? It's melting, okay, and then it melts to liquid form, and then boiling or vaporizing, I'm just put that there, and then gas, right? So our heat curve represents everything from states of matter to phase changes, and they talk about 2 specific conditions. No pressure involved here. Pressure is going to be what's on our phase diagrams, the ones with a little Y shape, like the curves. So this one's going to have temperature versus time. So time can be kinetic energy applied, because over some time you might apply kinetic energy or heat applied. There's different axes down here, but never pressure involved. That was a big misconception last unit. So as we go here, I want you to describe the motion of the particles at each segment. So generally, what would we say about solids? Motion-wise. Okay, what kind of motion that we just talked about? Vibrational. Okay, so they probably vibrate, and that's about it. They don't translate, they don't rotate a whole lot. There's not a lot of motion there. So what do you think about liquid motion? Right, well, they probably are vibrating and translating, right? They're moving around some more. They're a little more flowy. What do you think about gases? All three. They're probably vibrating, translating, and rotating. Now, I mean, the liquid phase definitely could be rotating as well, but I'm just trying to show you there's a difference in the amount of kinetic energy or energy motion as you go up the phases here. Sketch what these particles would look like at each stage in the heat curve. Maybe we'll do that. Explain what intermolecular forces have to do with the states of matter. So, what IMF, or what do you think, what could you say about the strength of the IMFs here? Strong, medium, or weak? Strong. They're holding those particles close together, right? They're not going to pull apart because they're so close together, they actually turn more of a solid type phase, right? So these would have strong IMFs. The liquid phase, what can you tell me there? Weaker, so let's go medium since we have another phase to talk about. So we have medium IMFs here, and gas, extremely weak. Actually, you know what? I'm not even going to say weak IMFs. What do we assume about ideal gases? Zero IMFs. We assume they have no interactions whatsoever. They don't even know what another gas particle looks like. They don't interact at all. So I'm going to say no IMFs. Now that's a stretch because we know that probably the real gases exist, right? Real gases are just, ideal gases are just help us sleep at night. So we can see that the IMFs, you have to overcome these strong IMFs in the melting phase to become a liquid. And then the liquid phase, they're still interacting. You have to overcome all of the IMFs here in order to go to gas. So this energy here and here, these are phase changes, right? We notice that the temperature is not changing on phase change. You see that? It's a flat. But here, we do have a change. What's changing here? We have time and or kinetic energies that's being added. So what's actually added here, we do have energy added, but the energy is not added to cause temperature change. The energy is added to do what from here to here? Do what? I heard kind of overcome. We're separating particles, right? So we're overcoming what? IMFs, right. So this energy applied here in the melting phase is not energy to cause temperature change, it's energy to separate solid and solid to make more of a liquid appearance, right? So this is going to have a name, and we talked about it last unit. We talked about enthalpy of fusion, so delta H of fusion. That is just a term that we use to talk about the energy required to melt. We were talking about that like first day of last unit. Energy applied to melt something from solids to liquids and kilojoules per mole. It'll come back to you because we're talking about that today. So what do you think this one's called? The energy that's used to vaporize something. So this is delta H fusion. It's just the name for melting. This one's going to be delta H vaporization. That. Okay. So these are just different names for the heat applied. So we're going to use this a lot today. This is a quick review of last unit, and we're going to kind of carry it into this one. We're going to add a little bit more to this, so hopefully you can have this out and let's leave some space around it so that you can add some more information. Woo! Okay, so let's start with a video. This video is going to explain more about heat transfer. And we talked a little bit about cubicles and cat yesterday, and then we'll jump into some problems. Okay, so video, I want you to write down 5 bullet points of information that you feel are conceptually relevant, like terminology, phrases he says, or whatnot. This guy, his name is, and I'll let you guys write this part down in just a second. Bozeman is the name. Super, super quick and easy explanations. I love it.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 47. It's on heat exchange. If I were to say, don't touch this iron right here in the middle, it's hot, what does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand, and that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion, or those molecules moving around. And we're going to have more energy in that than the colder body. And so a good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those two objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object, and we call that transfer heat. And so what we're really doing is transferring energy as thermal energy or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue, energy is being transferred as heat. That's
Okay, so energy is transferred as heat is what he's saying. When you think of energy, think of all the types of energy. Shout it out. All the types of energies you can think of. Kinetic energy. Potential energy. Thermal energy. What kind of energy is like from earth science? Nucleus. Nuclear energy. What else? Solar energy. What else? Geothermal energy. Hydropower energy. Convection and what are all those? Convection, radiation, conduction, those transfers of energy. So when we say energy, it's a really, really broad subject because there's just so many types of energies. So when you say energy is transferred, you kind of want to specify how it's transferred or what narrowing down your focus. So when you say energy is transferred as heat, it allows us to see, okay, this energy that's within the particles is transferred in a very specific way as heat. And we call heat Q. That's just the variable for heat. And it's usually measured in joules or calories. So we're kind of focusing more on the chemistry type of energy transfer versus geothermal or solar or stuff like that.
Really what's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this PHET simulation. So I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading apart. Likewise, when we cool it down, what we're doing is we're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down. But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button, and now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually reaches what we call equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. And remember, the Maxwell-Boltzmann distribution shows us how that works. If we were to look...
Or this from yesterday. We talked about this from yesterday. You drew a graph. So this blue one versus this hot one, this red one. The blue one is colder. Why? Why is it considered colder? Because, let's go for it, guys. Okay, so the peak is at a lower energy, lower temperature, and it's got, it's actually kind of hard to see because he's cut off the graph, but it kind of truncates right here. The blue has a lower range of energies. The red one goes farther. It probably goes all the way over here towards his face. So that longer range means it can access higher energies, aka hotter temperatures.
Look at it, this would be the cold body and this would be the warm body. Now in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. In other words, it's the same average kinetic energy on both sides. And that picture I showed you of iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance, and so we use a term called specific heat capacity to measure.
Write down specific heat capacity, and our units are going to be a little different. Where we use, so he has up here joules per gram degrees Kelvin. We use generally, in all the problems you'll use for me, joules per gram degree C. So I've really tried to specify Kelvin stuff will 100% go with gases, and Celsius stuff will go with thermochemistry, which we're starting now. So I'm just trying to keep them separated in your minds a little bit better. But he's going to talk about Kelvin, just deal with it for now, okay? Specific heat capacity.
Measure that. And so right here you can imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy, per gram, and then Kelvin, or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed, the amount of energy it has is going to change more readily than something that has a higher heat.
So what does a low heat capacity mean? It heats up faster, right? So you start heating a metal, it's probably going to be hot in nanoseconds, right? It's going to get hot real fast. You start heating water, how long does it take to boil water? 5 to 10 minutes, I'd say, right? It's going to take a little while. So the capacity of water being higher means it takes longer to heat. Good point to note, conceptual understanding, okay? So I'm trying to help you with that.
Specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold, the aluminum are heating up more readily than the water. Now the energy is going to be the same, it's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you learn to explain how heat exchange is due to kinetic energy transfer due to molecular motions? If you did, you learned what I wanted you to, and I hope that was helpful.
Okay, so that's our first video, and here's our first slide of information. So heat versus temperature, and I have another video after this, so I'm just trying to take care of you guys, so I think that's to do some calculations to get the hang of it, but here's intro. Heat versus temperature. We keep saying they're different, and you're like, well, why, Miss Enlow? Why? The real reason is heat we label as Q. Temperature we usually label as a delta T, or just a temperature T in general. That's one reason. They're two different variables. And the second is heat is going to be a sum of all of our energies. And temperature is the average of the energy, so kinetic energy in this part. So that's one of the biggest differences, sum versus average. So pretty much if you have two particles and they both have a high amount of kinetic energy, you add them up, that gets your heat. If you have two particles and one's 50 and one's 100 kinetic energy, the average of it is 75. So there's just a different mathematical calculation, but I do want you to know Q and T is how we do label them differently. So that's pretty easy. We just went over those definitions pretty much at the beginning, almost at the beginning class of heat, of temperature. All right, so let's look at a little bit more, and then we'll do our endo-exo video. You can always label KE for kinetic energy. Do not be writing out every single word on my slides. You guys have access to these if you want to print out the actual pages. Okay, so do not write this down. This is more, let's explain, okay? So right here in blue is the important part. We need to think of energy not as like a particle necessarily. It's just it's a form of energy that can be transferred, and you can account for it usually by temperature changes. You can't see it, you can feel it, right? So how do we know that energy exists? It can be stored in physical bonds. We talk about bonds all the time. Chemical bonds is the best way to store energy. So in the energy crisis that we live in every day, how are they trying to store energy? They're just making chemical reactions happen, and the chemical reactions that form the most bonds can store the most energy. So we try to store energy in bond form, but when we do a chemical reaction, we break those bonds, we rearrange those bonds, and so that releases energy or it stores energy. So there's a big change in how energy can be accounted for. You can either release it or you can store it. And we have to talk about that in terms of endo and exothermic reactions in just a second. And then we know that energy can flow from hot items to cold items and to the point until they're at thermal equilibrium. So flowing or transferring is was how we're going to reference heat or energy a lot today. And the last one, don't worry about that. Okay, so let's talk about how it's stored or released now. So 5 more points of information. Okay, this one we already talked about endo and exo a little bit, but this is a good, we have to draw some diagrams with them this time. So I want you to draw diagrams as we go. And I'll kind of help you and tell you what's important here.
Means heat.
Oh, sorry.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 33. It's on endothermic and exothermic reactions. If you understand that therm means heat and exo means to exit or to move out, it's pretty easy to break down these reactions. So an exothermic reaction would be one where heat is being released from the reaction. So a thermite reaction right here, you can almost feel how hot that is a reaction where we're releasing energy, releasing heat from the reaction itself. And likewise, if we have an endothermic reaction, that's going to be one where the reaction is taking in heat. And so in a cold pack like this, there's a combination of water and ammonium nitrate. That reaction is consuming heat, it's taking it from the surrounding, and so it's going to feel cold over time. And so you really have to understand what is the system and what are the surroundings. And so in a reaction, the system is going to be where the reaction is taking place, so in the chemicals themselves, and then the surrounding is going to be outside of that. So if we have a change in heat, that's either going to be an exothermic or an endothermic reactions. Now in the
Okay, so what he's saying is, and I'm going to pull up my thing side by side with his. What he's saying is that we have endo and exothermic reactions, right? So here's the system, and the outside of this stuff is the surroundings. Then we have a difference in heat because one of them is releasing heat or absorbing heat. So if usually what we are concerned about, become one with the system, okay? You are the system. You are the chemical reaction. That's really what we're honing in on and focusing on. So this right here, this system, we want to know how the heat is exchanged. So if the heat from the system is exiting, what kind of reaction is that? Exothermic, right? So we can actually, if it's exiting the system, then we can account for that because we also can measure stuff about the surroundings. So we can set up a reaction where you have area 1 and area 2, and if you can account for energy increase in area 2, aka the surroundings. If you can account for that, like with a thermometer, and if the temperature of the thermometer goes up, it's getting hot, that means it's an exothermic reaction. If the surroundings are giving up energy to the system, energy is going into the system, so what would you say? Endothermic. What would happen to the temperature of the external of the surroundings? It's going to go down. Temperature goes down out here because the system's taking in heat, the surroundings are losing heat. Because remember, heat doesn't just pop up out of anywhere. It's being transferred between substances. So if the temperature is going down in the surroundings, who's taking it? The system. So the temperature goes down. If the surroundings increase in temperature, that means the system's getting rid of it. The system's the heat is exiting. So the temperature goes up here. So we called those endo and exo last unit, so we're still sticking with those terms. But this is just basically what he's talking about. We think of two things, system and surroundings. Let's finish this.
We can't really see at the level of the atoms, and so we have to view it macroscopically. And we do that by simply measuring the temperature change. And so in an exothermic reaction, we're going to find that heat is being released from that reaction to the surroundings, and in an endothermic, it's actually being absorbed. Now, a really neat way to observe this is to use a model, is to use an energy diagram like this. And so the way it works is that the energy progress will be going along the x-axis, and then the amount of energy in the reactants and products is going to be displayed. And so in an exothermic reaction, what you'll see is a downhill reaction. In other words, the reactants are going to have more energy, than the products. Now, where is that energy going? Where is that heat going? It's going to the surroundings. And likewise, in an endothermic reaction, the reactants are actually going to have less energy than the products. And so they're consuming that energy. And so let me give you an example of that. Here's that exothermic reaction again. We've got a thermite reaction where we're taking iron oxide and aluminum, and we're making iron and aluminum oxide. Now, this is a really intense reaction, and it provides the oxygen in this form of combustion. And so this should be able to work even underwater. But if we were to look at the energy diagram of this over time as it progresses, we'd find that these reactants, the iron oxide and the aluminum, have a higher energy. In other words, there's more energy locked in those bonds than we're going to have in the products. And so we can see this as a downhill reaction.
So the downhill reaction is essentially, looking at the y-axis, you'll see the energies on the y-axis. Well, it looks as if reactants have high energy, and in the end, products have low energy. This is a full chemical reaction happening. There's this little hump in the middle, and we'll talk about what that means. But basically, if you have more energy to start with than what you end with, well, the energy had to have been released. And if you say released, you would call it an exothermic reaction. So you should identify that curve as an exothermic reaction. Thumbs up when you got this one. And I'm going to draw on here. I'm going to see if it'll let me draw. One extra piece of information. I think he might actually draw it, but I'm going to go for it anyway. So what is literally the difference in the energy levels? Well, it's just wherever the reactant energy is starting, and where the product energy ends. So the differences are these two blocks here. So the difference in energy, and I'm just going to try to draw. No. Darn it. Okay, I'll draw on mine. But basically, this little arrow here between these two lines, that's called delta H. Invisible ink here, okay? Delta H. Delta H is enthalpy of reaction, and that's what the delta H stands for. He doesn't like that I just drew on the board.
Now, what's going on? Why do we see this increase in energy here? Remember, we have to start pressuring those bonds, put a little bit of pressure on it before we can actually have them break apart and we get that exothermic reaction. And we call that a activation energy. So we're going to put a little bit of energy into the system, but you can see that we're going to net energy coming out of that. And so that's going to be measured in heat coming off that thermite reaction. Now, if we look at an endothermic reaction, again, this would be like solid ammonium nitrate, and we're just combining it with water, so we're going to make ammonium and nitrate ions. In that case, what we're doing is the reactants are actually going to have a lower amount of energy than the products. And so you can see here's our activation energy, but this is an uphill reaction. In other words, it requires energy, it requires heat. Where is it getting from that heat? It's getting it from the surroundings. And so when we're measuring
Sorry, you can see that a little bit longer there. All right, so you'll notice that this one's slightly, it's completely opposite. I was going to say slightly different. No, it's completely opposite. Our reactants start at low energy. Our products end at higher energy. Well, how the heck did we get more energy into the system? Well, we had to have added it. So adding energy is an endothermic reaction. So think way back to like last week. Endothermic reactions. Is that delta H a positive number or a negative number? Positive, right. Endo, add. So you're adding, so it's a positive number. Exothermic, you're releasing energy. It's exiting. It's being subtracted. So it's got a negative delta H associated with that. So I have two curves for you just like this. Oh, look, there's my lines. So they look like this one. So we just saw this one, just the last slide that he had up there. This was your endothermic reaction, and I just kind of put reactants as A and B and C as our product here. The difference in energy here to here, so basically the difference between product and reactant energy is delta H. And it's a positive number because it's an uphill battle here. So that's endo or exo? Endo. Okay? And then what he was saying earlier, he mentioned it on the exothermic one, he said there's this amount of energy you have to apply to pressure the reactants to break their bonds and, allow for some rearrangement of the particles and stuff like that. That energy is activation energy, to activate the reaction, right? So the reactants have to get all the way up to the tippy top here And that takes a lot of energy to get there. But after that, you know, once they meet this little activated complex, which is what that little point is called, they fall back down to products, which is a good thing, right? So the amount of energy that the reactants put forth to reach the tippy top is called E sub A. That has a name. EA is activation energy. Activation energy is literally the energy to activate the reaction. That's all that means. Nothing crazy, okay? So notice that EA is huge here, and then the energy that's required overall, this delta H is called, what is delta H called again? I heard it, kind of, enthalpy. This is enthalpy of reaction, or just enthalpy if you want to call it that. So those are two different things we're talking about, okay? All right, so the same story lies for exothermic. So we got our endothermic one. Okay, so exothermic. Ooh, this one's really crazy looking here. But bear with me, it's kind of fuzzy. We've got the reactants, uphill battle, fall back down to products. So what is this number 3 right here called? Activation energy. So this right here is EA. Notice it's smaller than the endothermic one. It's a pretty quick hill that it climbs right here. And so then if you're looking further, you'll see that we can identify the delta H of this one as well by just simply looking at the reactants and the products and the difference between those two. So this line that's labeled 2 right here, this is the delta H of the reaction, enthalpy of reaction, and for this one, negative or positive? Negative, because it's going down in energy, releasing energy. All right, so that's how we can graphically determine information about the enthalpy of reaction, or exo or endothermic stuff. Okay. So we already went. I'll talk about thermochemical equations again later. All right, so here's what I'd like to do. We're going to take 5 minutes to start ourselves a follow board. A lot of you guys did a fantastic job on that last time. We're studying before the test. I think that it helped a little bit with knowing our what are they called? Equations. So, come grab some paper. We're basically making 4 flaps. Okay? So come grab some paper. We're making 4 flaps. You can get scissors if you want. Take 3 minutes to make yourself a little window like this. Because we're going to do interactive notes versus just taking notes. You guys are going to run on a foldable. I got you. Does not have to be a Mona Lisa, so just make sure you can grab something, grab some scissors from my stacks over there. Aaron, there's scissors on that side. You guys can make a big circle with the scissors on the back of it. Don't be lazy about it. I'm trying to get you up. Is that a big deal? You're basically making 4 flaps. You're basically making 4 flaps. 2 on one side, 2 on the other side. They're on the back of this. Take 2 minutes and cut yourself some flaps. So basically you're folding, so you have there might be, well, it's okay. You guys can, yeah, there's a couple ones in here. But you'll be fine. No worries. It's a little smaller than I did, unfortunately. So just so you fold it in half, and then you fold each panel in half again and cut. You'll be fine. Oh, and Emily, you can have this. It's okay if it's a little one. I'm just trying to get you guys to help yourselves so you can study from this. That's fine. I want 4 sections. Just 4. 4 sections. These are the 4 sections. And what I have on the board is basically the 4 sections I'm going to be talking about today. take one more minute to get yourself organized, and then we'll start. Label your sections. This, and this. They're also on the board. These are the 4 sections, and I have them labeled 1, 2, 3, 4. But we're focusing on the content first. You guys can add some color and stuff later. Take a couple more seconds to get yourself there. And I have this printed for you, so you don't have to write down this information. We're going to do a lot of this during class. So basically, I'm going to talk about each of the equations we can use to do thermochemical equations. And within each section, we're going to talk a little bit about the variables used. You guys can later add a diagram or a picture, and I can help with that during notes. So if you want to take notes on a separate sheet of paper and add to this later, that's fine. Or you can try to take notes on the foldable. I'm just trying to make it more interactive for you. And then description of the type of problem, that's on you, okay? So I will describe the type of problem that you'd be asked in class, and then we're going to do some problems in class, and you guys can add to the foldable as we go throughout class or after class, homework, or whatever. I'm taking this up in your portfolio. So the instructions are a task already now, as well as some lecture problems we're going to start in just a minute. Yep, delta H fuzz. Just label your sections for now. Are there any extras, Josh? Extras? Everybody get one of these? Okay. Yeah, you did. Alright, so this is the stuff we're adding. You see the instructions on your paper I just passed out? Yeah? You see the instructions? Thanks. Okay, this is the big slide. Okay, you should have your stuff folded. You should have your four things labeled. I'm going to tell you information, and it's your choice as to where you're putting it, on your foldable or on some notes. So I should look up here too, okay? These are the couple of types of heat calculations we're going to do. I'm going to explain number 1 first. So this is Q equals MCAT, which is the first quadrant of your foldable, okay? So Q equals MCAT is what we talked about yesterday. These 4 variables, 4 variables you need to know. Q is, tell me what Q stands for. Heat. So I'm basically doing the first flap of the foldable with you. We're defining the variables. So Q is heat. M is mass. Okay, while we're defining the variables, let's define the unit that would probably be associated with that variable. So if Q is heat, what is heat measured in? Joules or calories, but we're going to stick with joules. I'd say 90% of the time I'm going to give you joules. You'll see a couple times the calories, like calories you eat every day, right? Mass is probably going to be in grams. C is our specific heat capacity that the Bozeman science guy just talked about, and he had it in joules per gram Kelvin. What did I say we would use? Yes, Celsius. Okay, so we're using joules, and it's like, you know, the R unit that had a fraction in it. It's joules per gram degrees Celsius. Joules per gram degrees Celsius. Let me see if I can scooch this down some. Sorry. No, just messed up. Okay. Okay. I just messed up a couple things. I'll fix it later. All right, so then delta T stands for change in temp. And yesterday, I told you a specific way we would always calculate it. How? It was something minus something. Yes, it was T final, so temperature final minus temperature initial. That will give us delta T, the change, right? And we just talked about this. This is measured in degrees Celsius. Okay, so we have the equation, Q equals MC delta T, but nobody says MC delta T, we just say MCAT because it looks like an A. So here's our equation. The other part of the foldable said to tell about the scenario in which this would be used. That is what this purple part is here. The scenario is, what's up? Question? T initial. It's like if you measure the temperature initial, like you just pop the thermometer in there, it's like, oh, it's 25 degrees C, and then after the reaction occurs, it goes up to 25, then it would be 20, or no, sorry, goes up to 28, so I think I just said 25. If the initial temperature of the reaction was like 25 degrees C, and the final temperature of the reaction was like 30 degrees C, then 30 would be our final, yeah, it would be T initial, 25, so the change would be 5 degrees C. That's basically what you do, yeah. Joules per gram degree C. Okay, so the purple part is what you should be writing for the scenario of the reaction. When when calculating heat, when it's not transferred, like it's not saying, I have a metal and I have water and I'm transferring heat. This is literally the heat of one substance. It's not in a scenario where it's going to be transferred from substance A to substance B or from system to the surroundings. So just simply the heat of aluminum or heat of water or heat of one special substance. Thumbs up when you got that. Okay, so I'll let you guys draw pictures on this one later. You can start, I'm going to scroll down just a little bit. You can start writing about 2, which is Q equals Q. It's the second quadrant right here. I'm just going to move a couple things down here. Oh, my lordy. All right. So this next section is called something special. It's called calorimetry or calorimetry. It's a special type of experiment we will actually set up tomorrow, and it involves setting up a situation where you have surroundings around the system. So you're going to have both systems and surroundings. So that's just kind of duh. We're going to be using both of them, and we're going to have them transferring energy between the two. So the scenario for this one, for the second flap, where you wrote negative Q equals plus Q. This is the scenario in purple right here. I'll give you guys a second to write that down if you've not already. Yes, Q of system equals, and I have Q of system equals equals Q of surroundings. One is negative and one is positive. And we'll talk about the difference between that in just a second. Oh, I just had calorimetry right there. And so we all know the law. We don't break the law. We said the law is a law of conservation of energy, just like we have the law of conservation of mass, because all mass has some sort of energy component to it, right? So we don't break the law. We always want to make sure we conserve energy. And so I love it. I saw this thing. I was on a Reddit or on the light switches where it says go green, turn off the lights, conserve energy. Joke's on you people, energy's always conserved. Do you know if turn the lights off or not? Huh? Okay, so I know. You gotta get that one. Alright, so we have the law of conservation energy, and energy for us is heat energy, so that makes sense. the energy that's from the system is transferred to the surroundings, but the exact amount of heat is transferred. So that's why we say Q equals Q, because Q, the system, let's say the system's losing energy. If it's losing energy means it gets a negative Q. So who's it given to? Who's it given the energy to? But who's the system giving the energy to? The surroundings. So if the energy is going to the surroundings, it gets a positive Q. It's just basically the negative and positive sign is telling us which direction the energy is flowing, in the system or out of the system. So you just have to be careful with your signs, though. That's because you can mess yourself up there. Now, if Q, we just defined Q. We just said Q was equal to MCAT. So I can give you a problem like this, and I can give you information about the mass of the system, the specific heat of the system, and or the temperature change of the system. And I could give you information about the surroundings. I could give you information about the mass of the surroundings, the specific heat of the surroundings, and or the temperature change of the surroundings. So if Q equals Q, one of which is negative, then MCAT equals MCAT. So I can give you, let's see, there's 6 variables, 1, 2, 3, 4, 5, 6. 6 variables here. I can give you 5 variables, like data points, and you would find the 6th one. But mass is measured in grams, it's easy to figure out which one's mass. T is measured in Celsius, it's easy to figure out which one's T. And then specific heat is measured in joules per gram degree Celsius. Good. So the calorimetry experiment we're going to set up tomorrow, it's like a styrofoam cup, because a styrofoam cup's a really good insulator. You'll drop like a piece of metal into here. The piece of metal is really smoking hot. Okay, already in that styrofoam cup, there's some water. So the system, so I'm giving you a drawing right now. If you want to write it, you're going to do it now. The metal is the system. The water that can, either give energy or absorb energy. This is water in here, and then my styrofoam cup. The cup is full of water, and it's the surroundings. So we're going to have some sort of transfer of energy between the two. And we'll see the difference by putting a thermometer in there to measure the heat differences, or the temperature differences. All right, I'm scrolling down in 1 second here. There's my quick, awful drawing, but you guys can probably do better. Okay, so in our next one, we have the third category. Q equals moles times delta H something. I put delta H fuzz, delta H diffusion. I could have easily put delta H vap or vaporization. I could have written both. But here's obviously the scenario in purple right here. That's your scenario you're writing down. Oh, I gotta tell you what. I'll use that. I just wrote down an extra note in green right here. Page 508 and page 522 have values that you might need from your problem set. So if you want to jot those down there in chapter 17. Those are the C values are on page 508 and the delta H values, which we're going to talk about on page 522. And they're different for every subset. So, we're going to talk about water 80% of the time, 90% of the time. So we'll probably accidentally memorize those values for water. But if you ever ask, what's the C for mercury? I have no idea. I'd have to look that up. So that's just FYI. All right, so number 3, calculating the heat when temperature is not changing. So the other two, we had a delta T involved, right? Temperature's changing, temperature's changing, temperature's changing. Boom. One where the temperature's not changing means we have a phase change. So we just had our little heat curve, the stair step. Where were the phase changes? Were they the slants or the plateaus? Plateaus. So there's a flat line, meaning delta T is not there. So if you don't have delta T, can you use MCAT? No, there has to be another equation, and this is the other equation. Q is equal to moles of the substance times delta H. Now, this is assuming delta H is published in kilojoules per mole. Normally, delta H is published in kilojoules per mole. So why does this make sense? Moles times kilojoules per mole. What is Q going to be measured in? What canceled? Moles. If you have moles times kilojoules per mole, moles cancel, leaving you with kilojoules. Was that a unit of energy? Yeah, totally. Yeah. Joules or kilojoules are going to be our units for how we express Q. So that's assuming that we have it expressed in kilojoules per mole. Sometimes you'll have a H value given to you that's in grams per mole, joules per gram. So like, for example, the heat fusion for water is either 334 joules per gram, or, from memory here, 6.01 kilojoules per mole. It can be published either way. So, if you have grams given to you in the problem, and you want to use this, it's fine to say, if you have grams given to you in the problem, and you want to use this, it is fine to say Q is equal to grams times delta H in this form. But if you're given moles in the problem, you can convert it to grams and use this first guy, or you can just stick with moles and use Q is equal to moles times delta H this way. It's up to you, whatever floats your boat. But you'll always be given these values. Okay, don't worry about that. This is the same thing, but delta H of fusion or delta H of vaporization. The numbers up here are different, but the process is the same. Thumbs up when you got all this stuff. Huh? You can write those numbers down now if you want, but I can always give them to you later. And we just talked about specific heat, so I'm not going to dwell on the definition. All right, we're going to do some practice problems, okay? So we're going to do at least one of each of these types, because that's what you need to know to be able to do for your problem set tonight. Okay, so on your printed notes, oh, I printed this on the wrong side. I printed chapter 17 problem set for you. Yay! It's right here next to your foldable, okay? No question. If I ever ask for you to start your homework in class, it's there for you. Okay. So we're gonna do on the back side where it says honors chemistry unit 6-ish. Okay, because we're in like unit 5.5. We're kind of between units right now. Chapter 17 lecture notes and practice. We're gonna do that first one together. We're gonna do one from each of these titles. So we're gonna do a Keegan cat, calorimetry, and a phase change. Okay, so we're gonna do at least one of each. Yes. Oh no! That dang copier. Who doesn't have a back side? You guys, what's up?
So over here right now we're going on to the last one.
No, we're not. We haven't talked to the last slide yet. So these are example problems about everything we talked about thus far. Okay. Here, go ahead and write down the C. Separate or someplace else. Write down the C for water. Okay. The specific heat of water we are using exclusively on most problems. So I just want to make sure you already have that down. So the C will be published as 1 calorie per gram degree C, or 4.18, you can all have to write 186, you can just prompt for 4.18 joules per gram degree C. So these are the two ways to express the C for water. It's an extremely high value of specific heat. Most metals, it's hard to see this table here, most metals are like 0.4, 0.5, 0.6. They're really, really low specific heat, so they heat up super fast. Water does not heat up that fast. Like, I would not go swimming right now in the ocean. It has not had enough time to heat up since the cold winter, right? It just takes a long time to heat up. So we're going to use this one a lot today. Here's your first question. I'll write it on the board in a second. Okay, so that value we're going to use a lot. I want you to first define your variables. Defining your variables is so important because then it will narrow down which of these equations you are able to use, because you can only use the stuff you have variables for. So a piece of stainless steel weighing this, what does that give us? Come on, how much you guys know? Mass, right. So mass is 1.55 grams of steel. I'm just going to put the steel there just to set on if I'll need it or not. I'm only doing one or two of each example type, so make sure you're writing these problems down with me. It absorbs that. What is that? Okay, so it's endothermic, so we know it's a positive what? What variable is this, guys? It says heat. Q, thank you. Q is a positive 141 joules. It's positive because it's endothermic. It says it absorbs. So a piece of stainless steel weighing 1.55 grams absorbs 141 joules of heat when its temperature is increased by 178 degrees Celsius. So when its temperature is increased by that. So what is that telling us? Change. It's telling us the change. It says it's increased by. It's changed by delta T 178 degrees Celsius. No need to go crazy and go Kelvin. Okay, we're sticking with Celsius for this one. So what is specific heat variable again? What are we looking for? We're looking for C. Okay, it's very obvious now. Which equation are we able to use? First one, Q equals MCAT. So all of this information is going to be applied in Q equals MCAT. Now, before I start plugging in all my numbers, it's really easy to make a slip up and put the wrong number someplace, right? I like to rearrange my equation first, just like we did Q equals RT. Arrange this first to solve for C. What do? Divide by MAP. Thank you. M delta T. Divide by MAP. M delta T. Okay, there we go. That's how I always say it. So these go out. So therefore, C has been isolated. C is equal to this stuff. Q over M delta T mapped. Okay, now I can plug, right? Let's do it. Q, what is it? 141 joules divided by 1.55 grams. That can be multiplied by 178 degrees Celsius. Plug that into your calculator or your phone or something. I want to see if you guys get the right value, because we have a problem with denominators. If you have something multiplied in the denominator, you've got to put like a bracket or parentheses or multiply it first or something and then divide. You can't take 141 divided by 1.55 and then just randomly times it by 178. You get the wrong answer. What is it? That's right. C is equal to 0.511 units. Degrees C. Okay. None of the units canceled, which helps because, degrees, nothing. Specific heat. It's got tons of units, so we didn't win anything to cancel. This is our final answer. Done. Questions on Q equals impact? I'll let you guys practice when you're in a second. Yeah. Yeah. Now, if by chance I give you two variables and we're talking about water, I need you to know the C for water is 4.18, or I can tell you, like, I might in the problem and neglect it to once because it's just so commonly used. But yeah, I'll always give you 3. Okay, let's go to a harder one. The Q equals MCAT, the first section of 5 questions, super easy, okay? Let's go to a harder one. I'm going forward, ready? Okay. All right, so now calorimetry. This is the next set of 5 questions. This one takes a little bit more effort. You're usually given 5 pieces of information, and you have to read a little bit to figure out what the heck you're doing. So here's me reading and writing down my givens. This is very important. What is the specific heat? Question 1. This is my question. What is the specific heat? And I like to go ahead and set up an MCAT table because the Q equals Q was MCAT equals MCAT, one of which is negative. So we're going to be given 2 M's, 2 C's, and 2 delta T's. So I like to go ahead and set this up first because I know I'm going to need all that information. One of these is going to be my question mark though. So I'm going to say, when I'm reading, what is the specific heat of 50 grams of a metal? So whose C am I looking for? As you kind of keep reading, you'll see we're talking about water as well. So I'm looking for the C of the metal or C of the water? Metal. So I'm actually going to label this one metal and this column water so I can identify and keep my MCAT stuff separate. It's really helpful, okay? This is how I did it when I was your age. I've been pretty good with chemistry since then, so just trying to give you some techniques, okay? So my question is the C of the metal. What else do I know about the metal right now from the first sentence? 50 grams is my mass. What else do I know from the first sentence? What is that? You said on the end? Oh, hold on. I got specific heat of the metal. I got 50 grams of metal. That raises 100 milliliters of water. What is that trying to tell me about water? I know it looks like volume, but it can be converted to mass. What is the density of water? 1 gram per 1 milliliter. So if I say 100 milliliters, how many grams is that? 100 grams, thank you. So we know the mass of water, 100 grams. Okay, so it raises 100 grams of water in a calorimeter from 34 to 36. Who is this information pertaining to, water or metal? Water. So this is about water. What is the delta T of water? 2. Because you're going T final, which is 36, minus T initial, because it says starting at 34, it's going to 36, so you're minusing the T initial of 34. So that is 2 degrees C. And I know you can do that in your head, but I'm just intentionally trying to write T final minus T initial for you. Okay, the initial temperature of the metal was 95. Yeah.
Can you have a negative change?
Yes, because one can decrease it, because that has to happen. One decreases in temperature while the other one increases in temperature, because that helps show the transfer of energy. Yeah, one will always be negative. Okay, the initial temperature of the metal was 95. The final temperature of the metal and water is 36. So what am I writing here? What am I writing first? 36, because this is T final, this is the end point. 36 minus what? 95, which was the T initial for the metal. Okay, so what's that temperature change? Negative 59 degrees C. Okay, notice the delta T's are different. That is okay. Delta T is not heat. The energy law is heat is conserved, not delta T. Temperature doesn't have to be conserved. Temperature is totally different than heat. So what is this variable I just told you earlier? 4.18 joules per gram degree C. That is our specific heat capacity of water. Okay, so now we have one variable we're looking for. We're looking for the C of the metal. So here's how I always set this up. We got a lot of information to deal with. So the very first thing is I write out my variable of negative Q equals positive Q. But I'm going to label which is which. Who is losing energy, the metal or the water? The metal, because it's decreasing in temperature. So, temperature and heat are directly related to one another. So it's decreasing in heat energy as well. So the negative is going to go with the metal. So I like to label that metal. And the positive Q is going to be associated with the water because it's gaining energy. So that's just identification. Then you go, I can't use Q and Q. MCAT equals MCAT, so this is essentially saying Q is equal to Q over here once I get all my variables plugged in. But I can't use Q essentially. I've got to use negative, what's Q equal to? MCAT, so negative MCAT equals positive MCAT. So this is for the metal, and this one's for water. Now, like I did earlier, I like to isolate my variable because, look, I know I'm going to make a mistake. I got 5 numbers to plug in. I'm going to make a mistake. So which of these variables am I isolating? C of metal. So I'm dividing over here by what? Negative, yeah, the negative. Negative mat for the metal. I'm going to keep putting metal down here so I know, when you say M, you're like massive water, massive metal. You don't know. So you got to label it. And then, so I'm dividing both sides by the same thing. So negative mat of metal on this side. So now we're all hunky-dory, okay? This negative cancels, this M cancels, this T cancels. I've got C of the metal that I'm looking for is equal to this big shebang. Woo! Lots of information to plug in. But if you keep your labels and your variables kind of organized, it's not too bad. So that's what I'm plugging in. So I'm going to start plugging in now. So I have a positive. What's this M referring to? Mass of water. What's the mass of water? 100 grams. Okay. Times C of water, which is 4.18 joules per gram degree C. Delta T of water, again, which is 2 degrees C. Good. So if you don't label who's water and who's metal, it's hard to figure out which variables are which. Okay, so over negative M of who? Metal, so that's 50. And delta T of metal? What's delta T of metal? Negative 59. So what are these negatives going to do? Cancel each other out. Good. The specific heat capacity C values, they're never negative. They're always representing like the amount of heat that you need to raise 1 gram of that substance by 1 degree Celsius. It's always a positive number. So if you had a negative C in the end, just cancel out the negative. It should have been gone. Okay? So this is how we have to plug in our calculator. Just simply take this top numerator, find out what it is, take the bottom denominator, figure out what it is, and then divide. Tell me what you got when you get there. If you participate in this, you will fix all your misconceptions about how to calculate. If you don't, that's on you, on your test. .283. I got .284 because I used the 1.486. So just, it's okay if you guys are a little off from me. I just go, I have different constants memorized. So if you got .283 or 284, as long as we're close, we're in the same ballpark of one another, we're in good shape. So there's the specific heat capacity of a metal. And you should know you're right, because metals all have really, really, really low specific heat capacities, okay? So like under 1 is probably a good number for a metal. Questions here? Thumbs up when you're good to go on. We have one more type of question to go on to. All right, so we got fuels MCAT. We got the calorimetry ones where you set up the heat transfer and you show that they equal in terms of their Q values. And you have your little box of data, which is extremely helpful. Now we're going to go on to a phase change one. I like the phase change ones. The only one I wanted to mention on this one is this is number 2 on your sheet. You see number 2 on your sheet with rhenium? Yeah? If this one's given to you in calories per gram degree C. Just pretend it's joules, but you're going to be noticing it's giving them calories. So I just want to point out that it's okay to see calories. It's another unit of energy. Okay, this one, where's this on your paper? Is it number 1 under the last section? Okay. All right, so number 1 under the heat phase change section, I have a graph for you. We might use it, we might not. So I want you to know in these problems you might have to draw a graph. The graphs are very helpful depending upon the temperature changes that occur. This one's not too bad though. How many grams of water, so question, grams of water at 100 degrees C and 101.3 kilopascals. Did we talk about pressure at all in this unit? No, this is a standard convention. Any problem that's talking about phase changes always gives a pressure. Nobody cares. That's just how it's given. Like when you say, I don't know, you want a soft drink at a restaurant. They don't ask you if you want ice. They just give you ice. It's just something that's always given. All right. So this is just a standard. Do not get confused by it. Could be vaporized. Vaporized. Vaporized means going from what to what? From what? Liquid to gas. Okay. Liquid to gas. Which delta H is associated with that? HVAP. Thank you. Delta H. VAP. All right. So how many grams of water, blah, 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 can be vaporized by the addition of that? What is that labeled as? What are they giving us? Energy heat. Q. Q is 180 kilojoules. All right, so we really have minimal information here. We have Q. We have delta H VAP, that's what it's talking about, and this is a variable value I would always give you. So what do you want to ask me for right now? Miss Emma, what's HVAP? Oh, here, guys, I got you. It's 40.65 kilojoules per mole. So delta H VAP I would always give you. Okay. So what equation uses Q, delta H, and it's asking for something with like, you know, grams or moles? Okay, so the equation is on the board. Thank you. It's I'm just going to write over top this thing. Q is equal to moles times delta H, fusion or vaporization. I just chose to write fusion in this one, but we're obviously using vaporization because that's what it's talking about here. Okay, so can we plug in this information? Can we get to moles? Yeah, and then what do you want to do? What's the question? Grams. You want to get to grams of water, right? It's still talking about water. So I want to go ahead and divide by what to isolate? Delta HVAP. So divide by delta HVAP. So my equation is moles is equal to Q over delta HVAP. Now I can plug in. Moles over delta HVAP. I'm sorry, Q over delta HVAP. I'm not sure what I just said. Q is 180 kilojoules. HVAP is 40.65 kilojoules per mole. What unit cancels? Kilojoules cancels here and here. I know it looks funky, but the mole being in the denominator of the denominator, when you do your floppy dot chop thing, it comes back to the top. Okay, so it's actually a numerator. So moles is our final unit here. So you take these and divide. 4.43. I don't know why I have this written. Oh yeah, sorry, it's right here. Wait, I can't find my answer. Moles are equal to 4.428 moles of water. So then that's not our final answer yet, but it's close. What's our last step? Convert to mass. What's mass of water? What is it? It's 18.016. 18.016 grams of water over 1 mole of water. It'll give us something like about 80. Yeah. 0.7 what? 78. Okay, so I'll go around that. 79.78. So let's go to 8. Because I think only had 3 sig figs throughout. So this is in grams of water. There's our final answer. So basically the phase change ones, you really just got to read it to figure out what the phase change is. If it's heat of fusion, you use one constant. If it's heat of vaporization, you use another constant. I'll give you the constants if I don't at first. I'll always give them to you. Just ask me. And then I want to do one more like this because this is the easier types of phase changes. I'm going to do a little bit more difficult one of phase changes. So let's do one from your set. Let's do number 4. You guys start reading number 4. Number 4 under that little phase change set. Oh no, I'm sorry. This is number 4, right? This is number 4. Yeah, sorry, I just have it labeled 3 for some reason. All right, now I have a legit phase change, a heat curve here for you for a reason. It has a purpose on this model also. So our real question is how much heat is required? So question is Q. We're required to change. What is this data that's given to us? So what would you call that variable? M, yeah. M is 52.9 grams of ice, or which is just straight up H2O. Okay. And we're taking ice to steam. Wow. We're going from solid through liquid to gas. And we're going from a negative 15 degrees C to 230 degrees C. So we have a lot of stuff to consider in this one. This one's kind of a cumulative final for us here. We have to go from ice down here at what temperature? Draw yourself a heat diagram or a heat curve if you've not already. Just do a quick sketch there. What is the temperature down here of this ice? Negative 15 degrees Celsius. So we're going to have to heat the solid all the way up here. We're going to have to melt it. We're going to have to heat the liquid. We're going to have to vaporize it. And then we're finally going to get up to the tippy top temperature that they told me of what? 230 degrees C. So this one's a bigger example because it's very cumulative. Whenever the temperature is changing of water, we have a what associated from the from the y-axis. What do we know? What's this temperature right here, guys, of the melting point of water? No. 0 degrees Celsius. Okay. So what do we know right now for this first segment? We know change in temp, delta T. We know delta T. What is delta T here? 15 degrees, right? T final of 0 minus a minus 15 is just straight 15 degrees Celsius. Okay. What did we write on the very, very first heat diagram we just drew at the upper warm-up? What did we write right here? Melt, and then we wrote on top of it delta H of fusion. Okay, so I can't use a delta T equation there because there's no delta T. What equation comes to mind for heat for phase diagram, for phase changes? Sorry, to find heat. Q equals moles times delta H of fusion. Okay, what equation comes to mind when you are using a delta T? MCAT, right? Q equals MCAT. Okay, so you're going to see this repeat now, okay? So if I want to find just the Q of this ice heating up, I would find Q equals MCAT. If I want to find just the Q of the phase change here, I have to use Q equals moles times delta H. If I want to find the next one, what equation do I use? Q equals MCAT again, okay? But what's the delta T on this one? I'm sorry, it looks like I put the 230 right there. I didn't. Ow. What is this temperature at which the water starts to boil? 100. So this one's 100. So what's the delta T here? 100. So I'm going from 0 to 100. And then I gotta account for the vaporization. Right? So Q is equal to moles times delta H vap. It's just the vaporization value versus the fusion value. And then I gotta go a little higher. I'm just gonna extend this up. This one ends over at 230. So what is this equation I'm using on that slant? MCAT, right? Q equals MCAT. What's the delta T value? Huh? 130, right? So from 100 to 230 is the difference of 130 degrees. How many Q's are up here? Count them. 5. Q1 is when ice gets heated. Q2 is when ice melts. Q3 is when liquid water is heated. Q4 is when liquid vaporizes. And then Q5 is when that gas gets up to the top temperature of 230 degrees. It just gets heated more. So how many calculations are we going to have to do? 5. And then how would you find the total heat of this one? Add them all up. So I'm not going to go through and calculate this one if that's okay, because I just went through how to do all this. So if you can find MCAT, basically taking, I'll do one example of each maybe. So Q1 is going to be, what was the mass of this problem? 52.9 grams. The specific heat of ice. Now this is a special one. Oh, you guys probably, you know some how these values. C, C, C. C for solid ice, C for liquid water, and C for gaseous water. They're all slightly different. What was the C for liquid water? You just write it down. 4.18 joules per gram degree C. The C for solid water is not something that I will ever have you memorize, okay? Is 2.05 joules per gram degree C. And the C for steam, which is gaseous water, is 2.02 joules per gram degree C. So what C are you using down here in the first one? Solid ice, right? So you would say 52.9 grams times the solid ice one, 2.05 joules per gram degree C, times, what's the delta T for the ice changing? 15. So you've labeled it here, 15 degrees C. So that's how you get Q1. One second. Q2, you just have to take those 52.9 grams to moles, and then multiply by delta H of fusion. Delta H of fusion I'll give you again. You just wrote this down at the very beginning, but it's 6.01 kilojoules per mole, or, you could get the joules one, but this is kilojoules per mole, and delta H of vaporization is 40.65 kilojoules per mole. So these are little just constants you would need on this problem. But basically, multiply, add all the Q's up together. That's our total Q. You have 2 problems like this. Number 3, I just set up for you, and number 5, I think on that one. Question, Jerry? This is all for water. And I would say 95% of these problems are water. If I ever give you something else, I would give you the values again. So yes, most of your problems will stay the same. Okay. We have about a little less than 10 minutes left. I would start with the Kegels and cat examples at the top of the paper. Ask me questions on those before you go. You should be able to finish I want you to do I want you to do 1 through 10. We'll save the other ones, the very cumulative hard ones, for tomorrow, okay? So you're doing the first 5 from the Kegels and cat one. We already did number 1. And you're doing the next 5 from the calorimetry ones, but we already did number 1. So you have 8 problems to do for homework, okay? Start now. Yeah.
There's only 4.
4 in the first section? I'm sorry. Sorry, so you have 7 problems for homework. Yay! Okay, those are done for sure tomorrow. After that, you can start the other ones, but that's on you, because we will have a little time in class tomorrow, but we also have a lab. I'm sorry, not 1 through 7, 1 through 9. Yeah, so just do the first 9, because we already did the first 1. So please get at least 1 to 2 problems done right now.